Day 2 of Kafka Summit San Francisco is officially open. Please welcome back to the stage today's MC, Head of Kafka Developer Experience at Confluent, Tim Berglund.
Good morning. How was everybody's day yesterday? Great. You're thinking, well, Tim, yours sounded like it was pretty good. Yeah, I'm not really sure what happened. This was not shouting last night, just kind of lunchtime yesterday. My voice decided to leave, and sometimes that happens. And when a thing like this happens, you start to find out who your friends are. Like my friend Shant. I'll let you read that quote. Yeah, Shant thought this was funny. And my friend Danny, she said, "Hey, wait, you sound like Distributed Systems Batman." I kind of like that one. It's like, which partition is the leader? Tell me. Like, I can't do that normally. This is great. My friend Michael, and actually various others, said this is finally what it takes to shut him up. This is your chance if you want to say something and I can't really talk back. And then finally, my favorite, I think perhaps most accurately, Neha Narkidi, my own boss. You sound like a frog, and I think there's something to that. Anyway, let's get the morning going with my few precious moments of speech ability. As a reminder, in case anyone did not get on the wireless network yesterday, you do need the password. That password is streaming. The SSID is fairly obvious. I'm sure you found that, but streaming is the password. Please get on. I've had great luck with the network, by the way. I installed a bunch of software updates, downloaded some videos, and no, I didn't. But as always, be a good citizen, right? If you're going to open up your laptop, like turn off Dropbox and do all the good citizen conference things, but this is a pretty great wireless network. I've had great luck with it myself, so please use it. Make sure you're using the app. I haven't had a chance to check yet, but I trust many of you have been rating sessions, posting pictures, doing what you're supposed to do in the app. Everything, by the way, is gamified also, so you may notice that you get awarded points for things, and just be advised of that. So please, I think the most important thing, if you're not going to do anything else, is please rate your sessions. That's great feedback for us to get. And if you have noticed the wall, that mosaic wall at the end of the expo floor, you guys have been active and very faithful in using the hashtag, tweeting pictures. I appreciate that. That picture is really shaping up nicely. Don't stop. Please keep tweeting, keep Instagramming. Kafka Summit is your one hashtag. That's all you need. It's just that hashtag. So please keep that up. And I must always thank our sponsors, without which this sort of thing would either not be possible or would be a lot harder to do at this scale. So thank you to all of these folks. Many of them are exhibiting here, so please stop by and say hi to them. And if you have a need for the stuff that they do, talk to them about it. That'd be great. Now, our first keynote this morning is by a man whose name many of you will likely recognize. And I can say for myself, since in my work here, I actually spend a lot of time talking to people about streaming and about Kafka and trying to get these ideas into people's heads. And I find that one of the messages that is the most successful and that resonates most with the developers and the architects I talk to traces directly back to our first speaker this morning, and that is Martin Kleppmann. Martin, welcome to the stage.
Good morning, everybody. I hope you're all well. I want to discuss this slightly provocative question, maybe. Is Kafka a database? What do you think? Is Kafka a database? I mean, some people will just immediately turn around and say, well, duh. Well, if you look at it, it has no tables, it has no data model, it has no secondary indexes. How on earth do you think it could be a database? The only thing you can do with it is subscribe to streams. And okay, I mean, that is all right, but I'd like to go a little bit deeper in this talk and see what we can figure out around this question. So in order to do that, first of all, we need to decide what is actually a database. What do we mean with a database? What is it that makes a database a database? And for the sake of this talk, I'm going to use the following definition. A database is a thing that has ACID properties. So some kind of piece of software that has these properties. You're probably familiar of ACID from the world of relational databases. These are the properties that we want a transaction to have: atomicity, consistency, isolation, and durability. And what I'm going to show in the rest of this talk is go into each of those letters individually and see a bit in detail what it means and how we can use Kafka to actually achieve those properties. So let's start with the letter D, with durability, because that's in many ways the easiest one to deal with. So back in the day when this acronym ACID was coined, this was in the early 1980s, back then durability meant that you write your transaction log from your database to an archive tape. And that means that, even if some problem occurs with the database, you can restore it from this tape. Nowadays, of course, tapes have fallen somewhat out of fashion, so durability got reinterpreted as meaning, well, we write to disk, we do an fsync to ensure that the data has really hit the disk platter, and now because this is non-volatile storage, even if you lose power to your server, you can expect the data to still be there on that disk. Fair enough, and so fsync is part of it. It more recently has also become extended. The definition of durability has become extended to include replication, and that is, not only do we want the data written to the disks on one machine, but we actually want it copied across several different machines, so that if you lose an entire machine, you don't lose the data. You can just switch over to using the copy of the data on a different machine. And so both of those, Kafka will do perfectly well. Kafka will write all of the messages that you publish to it to disk, and it will replicate those messages across multiple machines. So the only last part to durability, I would say, is, well, generally, if you want to be sure that you don't lose any data, it's considered a good idea to back it up and to have some kind of backup and restore processes. Of course, you would do this with a database if the database contains important data. So likewise, if you have important data in Kafka, you would need to back it up. But that is an external process outside of the software that you set up. So with that, I think we can basically tick off the durability. I think Kafka provides durability. There's not too much to argue around that. Let's look next at the A. So the A in ACID stands for atomicity. And there's a little bit of confusion around what this means, because if you're familiar with multi-threaded programming, for example, you get things like an atomic increment, or so an atomic compare and set operation, which are about concurrency. But the A in ACID is not about concurrency. It is the concurrency is actually under the letter I. Rather, the letter A here, atomicity, stands for how we handle faults. Like if something crashes, for example, or if a server loses power suddenly, or if things become disconnected from each other, what happens in that case? So atomicity is about handling faults, and we'll come back later to the letter I, which is about concurrency. So the intuitive idea of atomicity is we want either all or nothing. That is, if a transaction writes a whole bunch of different things, and then something goes wrong, something crashes, for example, we want either that the transaction is rolled back, and so none of the changes, none of the writes that were made in that transaction take effect, everything disappears, or alternatively, if the transaction commits successfully, then we want all of the writes made by that transaction to become durable. And so this is what we want of atomicity, that is this property that even in the face of crashes, we have either all of the changes taking effect or none of the changes. So let's look at an example where you might want atomicity. So this could be like any typical web app where you've got some data that you've stored in a database, but you might not store that data only in the database. You might also have a cache or some version, a copy of that data in a cache for faster access. And also you might store a copy of that data in a full-text search index in order to do keyword search, for example. And so you might use Postgres as the database, Redis as the cache, Elasticsearch as the full-text index, for example, or any other tools. And so what happens now if the user wants to change some data and different copies of that data live in these three different systems? So maybe this is an e-commerce site and you have a product catalog and you want to update the product description of a particular product. So that product description needs to be written to the database. And let's say you first write to the database and that is successful, okay. And now in the next step, you'll want to also update caches which contain maybe some kind of derived view or summary of the data in the database. And you also want to update the search index so that if people do a keyword search, they can find this updated description. And you can do this kind of thing, but let's say what happens if one of these systems is not working right now. So maybe the search index right now is having a bad time. Maybe a configuration problem, or its disks are full, or it's disconnected from the network, or it's just for some reason got into a bad state, or it's overloaded. For whatever reason, the search index is not accepting writes right now. So, okay, you've already written the data to the database, and you've written it to the cache, but now the write to the index is not working. So what do you do? Well, you could retry, of course. You could keep trying and hope that on the second or third attempt, the write may go through, but it might be that this service is just not working properly for an extended period of time. And so, well, you can't keep retrying forever. Maybe a better option would be to try and revert the write that you've made, so undo it again in the database and the cache where you've written it. But then what if other people have already seen this data? Now you're suddenly taking away data that has already been seen by other users. It kind of gets into quite a mess, really. And so the traditional approach that has been, research has always told the world what you should use in this situation is you want a distributed transaction. You want two-phase commit, which ensures that data is atomically committed across several different systems. So even if you've got maybe a database and a cache and an index all participating in a transaction, you can ensure with two-phase commit that if you commit the transaction on any one of these systems, then the other systems will also commit. If any one of them aborts, all of the others will also abort. So you get the kind of all or nothing, which is nice in theory, except in practice, well, most of these systems actually don't support two-phase commit. If you take Redis or Elasticsearch as the examples, they do not support XA transactions. There's no support for the Java Transaction API or whatever your favorite distributed transaction system is. So you simply can't do that. Moreover, even in systems that do support these distributed transactions, the performance tends to be pretty bad. The operational problems are pretty bad because it just takes one system to be running slightly slow, and then the whole rest of the system grinds to a halt. So it's not really great. So you might have heard me talk about this particular example before, and what I suggest to people is not, if you want to write data to these several different places, do not have the web application directly write to these 3 different places, because that gives you all of these problems. Instead, we can use a tool like Kafka, and we use it as follows. So the web application, if it wants to write some data to several places, it does not directly contact the database. Instead, it just writes an event, a single event that describes the data that it wants to write. For example, updating a particular item description in a product catalog. And it writes that one event to a log like Kafka. And so this is just a single event. Like a single event is either written or it's not written. No matter what kind of crashes happen, you will never get a half-written event in Kafka. So writing a single message, a single event, can be made atomic very easily. Either that message is written to the log or not. And then the database and the cache and the search index that you want to update, they all consume from this log. They independently consume this log. And for example, the database will take all of the events that you've written to the log that describe what you want to write to the database, and they will take those events and reflect those writes in the database. Likewise, the cache, it independently consumes this same log, and the search index, it also consumes this log. And the guarantee that Kafka provides us here is that all of the consumers will see the same events, and they will see them in the same order. And we can rely on this guarantee now to ensure that any event that appears in the log will eventually be reflected in the database and in the cache and in the search index. And now, if, for example, the search index is temporarily running slow because it's not working, that's all right. The database and the cache, they can still continue consuming this log without any interference from the search index. they can keep their systems up to date. And then at some later point when the search index recovers, it can restart its consumption from its last checkpoint, the last message that it previously processed correctly, and it will just go through the backlog, and it will see all of the messages. It won't drop any messages, and it will apply all of those to the index. So what we get here is atomicity. We get exactly the all-or-nothing guarantee that we wanted. That is, if a message appears in the log, then its effects will be written to all of these consuming storage systems, but we get it without having any distributed transactions. So this is a really interesting idea. Let me show you another example, just a moment. Another example of atomicity. So like this is the standard textbook example that you always see of atomicity, which is you want to transfer some money from one bank account to another one. And so in a relational database, you would do it like this. You start a transaction, then you update the balance of the account from which you're taking the money and, for example, reduce its balance by $100. And then you update the balance of the account that is receiving the money, and you increase its balance by $100, and then you commit the transaction. And now, it's really important that these two updates happen atomically. Either both happen or neither happen. Because if only one of the two happens, that would mean that either you've got money that is disappearing into the ether, or you have got money that is being created out of thin air. And both of those are things that are generally considered to be a bad idea in financial systems. So generally in financial systems, you always want to preserve money, only move it around, but never create or destroy it. So here in this case, we want the two updates to happen atomically. We know how to do this with a relational database and a transaction. Fine. How would we do the same thing with Kafka? I suggest the following. If you want to transfer some money from account 12345 to account 54321, what we do is we put a description of the transfer that we want to make in a single event, just a single event, a JSON document or something like that, and append it again to a Kafka log, to a Kafka topic. That is all we do initially. So this does not yet describe that the transfer has happened. It just describes the intention of we want to transfer money from this account to that account. And we include some kind of event ID in this event, which is just some kind of string that uniquely identifies this particular event. Now we write a stream processor. This could be, for example, a Kafka Streams application. And what it does is it consumes this topic containing the transfer events. And for each transfer event that it sees, it emits two output events. One output event is a debit. It says, I want to take $100 from the source account. And the other is an event for the destination account and says, I want to add $100 to this account. And so notice here now that these two events, they can actually go into different partitions because it might be a large system. There might be many, many different accounts. So what we want to ensure is that all of the transactions that affect a particular account number all go into the same partition. We can do that very simply by using the account number as the partitioning key here. And now this will ensure that all of the transactions that affect account 12345 will go into the same partition. Note here also that I've carried forward the event ID from the original transfer event. So this allows us to track the provenance, where the events came from. It allows us to see that this debit and this credit event are the result of consuming that particular original transfer event. And now once we have this, we can have a second stage of stream processor. Again, maybe a Kafka Streams application. And it just looks at all of the events that are happening for a particular account number, and it maintains a balance, and it maintains a transaction history. And so the stream processor will just take an incoming event for its particular account number and see, OK, I need to increase the balance by $100. So it records that, and it records the ID of the event. This recording the ID is useful because maybe the event might get duplicated. So it could happen if the first stage stream processor crashes, that maybe it has output only the debit event but not the credit event also. So you could get these kind of half-finished things happening if a stream processor crashes. But then, when the processor restarts, it will resume processing from the last checkpoint, and it will keep going through the transfer events. And because that transfer event previously was not completed, the processing of it was not completed, it will process that same transfer event again, and it will just output the same debit and credit events again. So you may end up with duplicate events, but for the second stage stream processor, it's easy to deduplicate those just by using the event ID. So in the jargon, we call this making the processing idempotent. Even if the message appears more than once, it just takes effect once. And then at the end, you can write the updated query balance to some database. It can be like a local state store within the Kafka Streams application, or it could be an external database. And this database is now being maintained correctly. It has exactly the properties that we want. It's atomic. So even if things crash here, we can be sure that if that original transfer event occurs in the original log, then the two resulting credit and debit will be applied to the two downstream accounts. But if that original event is not in the log, then of course nothing happens. So we get all or nothing. We get atomicity. That's all about atomicity. Let's move on to I for isolation. And so as I said earlier, this is about concurrency. Now, in relational databases, isolation is actually a bit of a mess, and there are a whole bunch of different isolation levels that people use. But the strongest level that people use is called serializable. And the intuition bit behind serializable is that transactions behave as if they had the database to themselves. So transactions behave as if they were executed one at a time in some serial order on the database by themselves. So it's as if there was only a single thread executing transactions, even though in reality you might have multiple transactions executing at the same time. So let's look again at an example how this might look in a relational database. Let's say you have an application in which users can create accounts with a username, and what you want to ensure is that the usernames are unique. And that is, you want to ensure that there is at most one account with a given username. There should never be two accounts with the same username. And so we can achieve this in a serializable transaction by first checking, is there any account for the requested username? Let's say the user wants to request the name Jane. So is there a Jane already? And if no, if that first query returns 0, then we insert a new row into the database saying this username Jane is now taken, and then we commit the transaction. And so this works fine if you have serializable transactions. Let's look at an example of the problem that happens if your transactions are not serializable. In that case, you could have one user that does the count and returns 0, because at the moment there's no username Jane. Then, around about the same time, a different user, the purple user, wants to create a username with the same name. So they also request for any existing accounts in the database. They see there's nothing there. Now, the first one, because it saw that there's nothing in the database, it goes ahead and inserts a new record into the database. And likewise, the purple user, it saw that there's no account for Jane in the database, so it also goes ahead and inserts a record into the database. Both commit, and now you've got actually two records, two user accounts with the same name, which is what we were trying to prevent in the first place. So this is the concurrency problem that can happen if you don't have serializability. How can we do something like this in Kafka? Turns out it's really simple, actually. So what we can do is we make a Kafka topic, which I might call username claims or requests for registration. And so any user, whenever they want to create an account with a particular username, they send a message, an event to this particular topic, and we use, in this case, the username as our partitioning key. And they send an event saying, I intend to register a particular username. This event does not yet mean that they have successfully got the username. It just says that they would like it, please. And so you might have these two users, both this greenish-blue user and the red user, concurrently wanting to register the username Jane. Now, Kafka, what it does is it puts all of the messages that you publish to it, all the messages that you publish to a single partition get put into a totally ordered log, and everyone who consumes that log will see the messages in the same order. And so of these two requests for Jane, either the red one will be first or the green one will be first. Let's say, for example, maybe the red one comes first. So now you can have a stream processor which consumes this topic of registration requests, and it keeps a little database on the side where it keeps note of which usernames have been claimed and which not. And so maybe the red user is the first one to appear in the log. And so then the stream processor will look in its database and see, OK, there's no existing username Jane, so I'm going to emit an output message to this other topic called successful registrations, saying red user has successfully registered the username Jane. And then a fraction of a second later, the message from the blue user gets processed. So it comes later in the log. And so by this time now, the stream processor, because the stream processor is just a single-threaded loop that goes through the messages in a single partition, one at a time, it, by this point, has registered in its database, oh, we already have a user called Jane, so that username is taken, so we're going to output a message to this other topic saying, sorry, it's already taken. So what we get here is actually a serializable execution of this very transaction, and we make it serializable by effectively putting this logic, this transaction, inside of a stream processor. And now, if you have a Kafka Streams application, the stream processors are just single-threaded pieces of code that loop through the messages in a partition. So it's trivial to make this thing serializable because it already executes these operations in a serial order on a single thread. So we get serializability. We get very strong isolation between these things. And we can still scale to very high throughput by putting different usernames in different partitions. And so they can be processed on different threads. So by having lots of partitions, we can still have lots of threads busy processing these things. So we've covered atomicity and isolation and durability. This really just leaves consistency. And the C in ACID is slightly different from the other letters because it's not really a property of the database. Rather, consistency is a property of the application if it uses the database, if it relies on the atomicity and the isolation and the durability properties of the database. So typically what we mean with consistency is that there's some kind of integrity constraints or some kind of invariance that we always want to be true. So the example of a username being unique would be an example of an invariant. We always want at most one registration with a particular username. But you could imagine a similar thing being in a bank account balance, you want it to never go negative. Or if you're selling seats in a theater or an aeroplane, you want to sell no more tickets than you actually have seats in the theater or the aeroplane. So those would be typical consistency constraints. And we saw, like we saw with the username example, how you can implement those kind of things on top of Kafka. If you think about the example with the account balance, you can actually implement that in a way that's very similar to the username example by serializing all of the requests to withdraw from a particular account through a single-threaded stream processor that just checks the validity of those requests. So I'm going to say here we can actually enforce very strong consistency properties on top of Kafka by building stream processors, which is really interesting. So I've shown that what we have here is we can actually make things that are not quite transactions, but using Kafka, we can actually preserve the atomicity, the consistency, the isolation, and the durability that normally we expect of databases. So does that make Kafka a database? I mean, you could say a different definition of a database is that you can query it ad hoc. This comic here did the rounds about 10 years ago when, like, at the height of the NoSQL hype. And it makes a fair point, which is, like, sometimes you just want to do ad hoc queries over some data and, like, just have it be easy to query using SQL or something like that. And admittedly here, if you replace the words distributed MapReduce function in Erlang with distributed K-streams stream processor in Java, then we actually have something that is maybe comparable. So I will take this criticism, but on the other hand, if what you want to do is ad hoc queries, this is actually really easy to do. You take your data in Kafka, you write it out using Kafka Connect to your favorite data warehouse, and in your favorite data warehouse, you can query it to your heart's content. So I'm just going to leave that to existing database software for doing ad hoc queries. What I rather think, what I've described to do today, is what we can do using Kafka and using these logs. It's a bit like having Lego bricks available from which you can build your own database. And the way we do this is we have to we have to change our mental model of how to program these things a little bit, because we're not really thinking in terms of transactions, but instead we're thinking in terms of these multi-stage pipelines with stream processors in between, where events flow through these several stages and get validated at different stages. So it's maybe slightly unfamiliar, but I think it can have very good properties. I think the reliability, the uptime of these systems can be excellent. I think the throughput and performance can be excellent. And we can actually get very strong consistency properties. You know, serializable transactions are actually a whole lot of distributed databases that don't even provide those. And we've seen today how we can do this kind of thing on top of Kafka. So that is why I find this a really interesting area to explore. And maybe if any of you are interested in trying to build systems along this way, I would love to talk to you and find out what kind of things you're trying to build and whether we can express it in terms of this log-based programming model. That's all I have today. I just wanted to say later on I will be giving out free signed copies of my book. I think we'll be doing that in the afternoon break at 3:30 down by the Confluent booth in the exhibition hall. So I would love to see you there. But in the meantime, thank you very much for listening, and I hope you have a great conference.
Martin, thank you. Thank you, Martin. That was fantastic. I think if I had asked you before that talk whether you thought Kafka had acid transactional semantics, you'd say, well, no. You know, like, it's like a bad joke or something. Now you're kind of like, wait a second, maybe it's more acid than the databases we think of at scale, even at moderate scale, the kinds of systems we actually build. So I think that talk is going to leave a mark and is worth talking about. What we're going to do next is a thing that we have not done before, as you can see by the flurry of activity behind me. Something special is going on. Our own, Confluent's own, Neha Narkidi, co-creator of Apache Kafka, co-founder of Confluent, is going to moderate a panel. And I would like now to welcome Neha and her panel to the stage.
Good morning, Kafka Summit. I hope you had an excellent day yesterday, and I'm looking forward to more amazing content. As you can see, I changed it up a little bit this year, and how could I not? I could attract these amazing panelists to come here and discuss some interesting questions with me. And not just any panel, but a power panel. Who do I have here? I have the CTO of Microsoft and my mentor. I have Martin Kleppmann. His book is amongst the top 5 books on Amazon under computing. I have my co-creator of Kafka, my co-founder, my friend, and Slack's infrastructure boss. Now, I don't think we should get into any more introductions than that, so let's get started. I have Jay and Kevin here, and I'm not sure many of you know that Kevin was head of infrastructure at LinkedIn back when we created Kafka. So I thought, what could be a better start than really having them walk down memory lane and reflect on Kafka's origin story? And no, by that, I don't mean the usual, why in the world did we name it Kafka part? But really, or what?
We've already answered that one.
Yes, we already answered that one. But really more about, I think people are in the audience here. They want to know, what does it take to create another Kafka? How do you create a successful technology like that and one that becomes ubiquitous? So Jay, why don't we start with you? Why did we open source Kafka? And can you share the recipe for creating another technology that goes on to become so ubiquitous?
Well, we had a number of open source projects, and not all of them became popular. So I don't know if it's a formula that works every time. Yeah, I mean, it was one of the things that we worked on that we probably had the highest hopes for. There was a lot of ideas floating around at that time. It was a time when there was a lot of problems around how you handled data and not that many off-the-shelf solutions for companies like LinkedIn that were working at scale. And so we were in the habit of building these internal infrastructure layers. There was a bunch of interest in kind of the stream processing literature. It seemed kind of weird that all the cool analytical processing happened like at the end of the day.
Right.
For a digital business, it was kind of like the end of which day. That didn't really make any sense. And so we were trying to think of like why had this academic literature not really caught on in the world. And we kind of felt like, hey, maybe the problem is people don't actually even have a way of getting access to the streams at all. And that was part of it. And then we looked at the architecture of distributed databases, and they had this kind of log-oriented structure, and that showed up in the stream processing literature, and it just kind of kept recurring. And then we were facing a lot of the problems ourselves, like there was an interest in these kind of data-driven applications. There was all the data pipeline problems, and so that kind of led to the creation. We had kind of a series of different technologies, some of which were kind of always falling over and needed to be replaced. And so that was how we started the effort. And then it took a lot to actually bring it to scale. It didn't work that well at first. It took a lot of effort to really make it something that could be trusted for critical applications and really scaled across the company.
I completely agree with you, and Kevin, I'm sure you will know, or you should share from a business perspective. As Jay mentioned, we had a couple systems to do, ETL into Hadoop and database change capture back at LinkedIn. So from a business perspective, why did it make sense to fund Kafka, and more importantly, why did you allow us to open source it?
Yeah, I mean, so those I think are really, they're almost two separate questions. And so on the latter, like why did we decide to open source it? So that was something that Jay was pushing for alongside his boss at the time, Igor Perisic. And like Igor has this really great post on LinkedIn about like why LinkedIn became an open source first company, like where just sort of by default, like if you were doing something there, and like this is still true today, that you come to ask someone for permission to open source it, the default answer is yes. There has to be a good reason not to open source it. Now that doesn't necessarily mean that everything you want to open source it's a good idea to open source it, or that moreover, if you do open source it, it is going to become a successful thing. But like it was just sort of an easy decision for us. Like it was the way that we attracted great developers to the company. Interestingly enough, it was like one of the cool pieces of marketing for me joining LinkedIn in 2011 before the IPO, because at my startup, AdMob, we had used Voldemort, which was a key value store that Jay.
Finally, we find someone who uses Voldemort.
Yeah, and so like we at some point had been looking for a key value store, and like we evaled a whole bunch of different stuff, and like we decided that Voldemort was the best thing, and I'm like, because it was open source, like we got this visibility inside of LinkedIn's engineering team. We're like, wow, these guys are like pretty cool, and like that had always stuck in my head as like I was sort of navigating my own set of choices about career. So like everyone should just go read Igor's post, because he sort of describes all of that. From a business perspective, like why Kafka made sense is, and this is something that I think every great engineer ought to be, or everyone who aspires to be a great engineer ought to be looking for as much as possible. So like what Jay described was like this sort of ecosystem, both inside of the company with things that we had built ourselves, as well as outside of the company. And third-party products is this sort of convoluted, complicated ecosystem of technology for moving, moving data streams around from one place to another. We had at least a couple of other things that we had built at LinkedIn to sort of power bits and pieces of our distributed data infrastructure. And what Kafka like really did amazingly well is it sort of figured out the simplest, most elegant way to express the general problem in terms of, like in a way that would allow us to sort of not only solve like these other sort of like distributed systems application specific terms, but like what it's done inside of LinkedIn is just ridiculous, like how robust the internal data ecosystem is because of Kafka. There are tens and tens of thousands of producers of data, and like on the other side of that, like, thousands of different consuming applications that do like a ridiculous variety of things. And so the reason that exists is because like Kafka is such a powerful and simple expression of a general idea. And so like when you see one of those, like as an engineering leader, like just invest. Like they're super rare, like MapReduce and some of the things that we had invented at Google, and like they are reliably like the best technology investments that you can make.
Wow, thank you for sharing that. In the same context, like you said, Kafka is used in a variety of different ways, right? And I remember that there was another transformation happening at the same time at LinkedIn when we were working on Kafka adoption, which was really us moving to microservices, breaking big applications into small little ones. You led us through that whole transition. So tell the audience what it took for LinkedIn to be successful. Like, was it painful? Was it easy?
No, it was super hard. For a whole bunch of like technical and cultural reasons. Like the technical reasons were, sort of harmless, I guess. Like there's it used to be a trend, around so LinkedIn was founded in 2003, and so at the time, like it was completely typical for folks to build intranet technology stacks using something that looked very much like a LAMP architecture, or like sort of an enterprise database architecture where you've got a monolithic app and a monolithic database, and you sort of get started that way because it was the easiest way to get your minimum viable product out. But like as we all know now, like that doesn't scale, and the transition from the sort of set of technology decisions that you have to make to like build things that way to like building in a microservices way are difficult but tractable. You just sort of have to have the willpower to like go do them, and like where you get the willpower is like having just sort of this culture of thinking about things. And like I think maybe the single hardest thing to do about that transition is like you have to think about every service in your microservices architecture as like a unit of accountability. So like you create it, you have to own this thing in production. You have to own the fact that people are going to use it in ways that you really hadn't intended. You have to basically get over this notion that you get to sort of vertically own your entire stack of services, and like you get to sort of control it in this very sort of waterfall-y, like monolithic way. And like that mindset, like getting past it is like a little bit difficult. It like feels scary to you. Like if you're used to being in control of everything, it can feel burdensome to you because like, oh crap, like now I've got this thing that I've got to carry a pager on, or like somebody's got to carry a pager on. I'm going to get like called at 2 a.m. on a Saturday night because it's down. And it sort of challenges your decision making because not everything should be a microservice. And so like lots of people, when we began doing this, would create these like pathologically bad microservices, not sort of accepting that it was like a unit of accountability. They're like, oh, this is easy to create. And at one point, you guys remember this very well. Right around the time of the IPO, we had more services in production at LinkedIn than we had engineers.
That's right.
It's just nuts.
I think it took a while to realize that wasn't good.
Yeah, yes. No, it's very much not good.
Not recommended. So not everything should be a microservice. Julia, as head of infrastructure at Slack, what do you think? Like, are microservices for everyone? And does Slack subscribe to that?
So I think it always depends, and it depends upon what you're building. And I think what Kevin highlighted on the culture that your organization has. So Slack is only about 5 years old, which is not that old, and we still operate a very large, was PHP, is now hack monolith. My organization runs a lot of services. I wouldn't necessarily say microservices, but I would say first-class services that the monolith connects to. And for us to understand how to bring those services to maturity, how do you tune it? How do you monitor it? Who carries the pager for those services? That's us starting to dip our toe into, OK, what does it mean to really own and operate services at scale? I think for a lot of reasons, our monolith will probably be around for a while. The founders of Slack, who I work very, very close with now, they know how to run PHP at scale. And our chief architect, Keith Adams, came from Facebook. We're now using HHVM. We know how to run this technology. At the same time, hopefully most of you in the audience, hard to see, but how many of you know what Slack is? How many of you use it? OK, thank you. Thank you. I appreciate it. Hopefully it's working fast for you today.
More than we'd like.
If it's not, you know who to come to. So a lot of the interactions within the product, they're very tightly coupled to each other. And so what that means is that when we've thought about potentially splitting the monolith, there's not a lot of services that we've quickly identified as being able to split out. So when you're interacting, switching workspaces, going to different channels, searching for users, some of that, there is some services you're connecting to, but largely there's a really tight coupling, and that doesn't yield to us like orthogonally splitting that monolith apart. Now, who knows what the future holds? Like potentially we might do that in the future, but for now we're operating a very small set of services. We're understanding how to, again, deploy, tune, monitor those services at scale, and then we'll see what happens.
Yeah, and you brought up that point, right, about the integration, right, between these different services. And so, Martin, you had a really good talk here. Is Kafka a database? So in the context of microservices, right, traditional NTR architectures, we've just treated the database as the sole integration point, right? That's where the state goes. So as you start to break these monoliths into microservices, as they start to become more like stateful and event-driven, like how does the role of the state store change? And what is the relationship between databases and stream processing then?
Yeah, that's a really good question. I think often, like if you're building services and those services are stateless, then basically life is easy, and so right. no problem, right? So the difficulty is then handling state. And moreover, if each microservice has its own database and it's a self-contained vertical slice, and when data of a particular type needs to be stored, you always go to that particular service and it just goes into that one database, then again, that's quite manageable. So where I feel the difficulty starts arising is if maybe several services need access to some data. And you could have them querying each other all of the time, but that can start getting rather slow. So you might then end up having a copy of some data in two different services' respective databases. And that's then a place where I feel stream processing can come in, because like if you're doing REST calls between microservices, that works quite well for read-only requests. But if you're doing writes, well, we have all of the problems that I was talking about earlier in my talk. Like you can have writes that succeed in one place and fail in another place, and now you've got a consistency problem. And so there, I think stream processing can really help by providing a kind of reliable pipe for transporting writes from one part of the system to another. So you can initially write something in one place, but then be sure that everyone who wants to know about those data changes, they can subscribe to the appropriate stream and be notified about it.
So there's this question that comes up pretty frequently. We get asked that. I'm sure Jay, you should weigh in. Is how when it comes to request response architectures and event-driven architectures, like does the event-driven architecture and where stream processing comes in, does it replace your request response? Is that really the the future that people are marching towards?
Yeah, no, I think these things both need to exist, right? Like it almost depends on the problem in the business that you're trying to solve. And so, if you have some user experience that's very much request-driven and synchronous, then that's probably going to trickle down to the technology you build. If you think about how a lot of businesses work out in the world, there's actually things happening in reality which take time and they're asynchronous. And if you think about the technology that results from that, it typically takes on this kind of event-driven path. Or it doesn't, and it gets kind of, pigeonholed almost into a request-response paradigm, which can actually be really fragile and hard to make reliable and correct. And so I think if you see, companies as they grow, often a small company will really just have one of these things, but as it gets more rich and the functionality gets richer, I think you always end up with, some amount of both of these things. It's very rare that everything is all one. In some sense, a lot of the early web companies, I think, were very request response heavy because they were ultimately doing some kind of CRUD. If you think about how does a bank operate, I think it's a lot less UI, right? There's a lot more happening kind of in the background in response to the interactions with customers, the trades, whatever the back end of that system is doing. And so I think these paradigms kind of naturally fall out. And if you talk to people who work in different companies, they often have in their mind some way that things work, right? And when people try and talk to each other, they often can't communicate because they're so locked in the paradigm that they come out of.
Right.
I mean, I think one thing to add there is, in a whole lot of ways, the pattern is sort of similar to the monolithic web app versus microservices decisions, and a lot of this is just sort of about scale and simplicity. So, as you scale, microservices is absolutely the right way to solve your overall architectural problem, and the question of how soon do you start going there is a matter of how simple are your abstractions for building microservices. The same thing is true for data systems. So at the smallest unit of scale, the easiest thing to do is solve your problem with a monolithic data store. But the things that Jay and Martin are describing are it's just unquestionably the way that you scale data systems is to break things apart and have these sort of message systems sitting at the core of them. If you look at a database architecture, that's the way that they're, that distributed databases are built. And so, it's the right and natural thing to sort of pull things apart, the same way that you pull your monolith apart into microservices. So, I think, you really should be thinking about, when, not if, with these sorts of things, especially as the universe of data explodes.
That's right. That's right. So switching gears a bit, there's a lot of talk happening in the community about open source licensing, right? And there's an obvious tension between open source, companies and creating, like Confluent, that create the software, get back to the community in a big way, and on the other hand, public cloud companies that resell open source software and often without contributing much back, right? Kevin, you've been on both sides of the equation, right?
Yeah.
At LinkedIn as the sponsor of open source, and now at Microsoft.
Yep.
How do you think this is going to play out? So in the end, the community continues to thrive and wins.
Yeah, look, I think over time, and you can sort of certainly see this with Microsoft, is that there's just a set of natural benefits for open sourcing data infrastructure and participating in open source communities. The most powerful reason you do that is because that's what developers want. It's just pure and simple developer choice, and it's the the right thing to do to serve your developer customers to sort of be involved in these open source communities as a productive, positive member of their their communities. The thing with folks who actually have public clouds, you're sort of selling cloud services, I think there's natural alignment there actually, and people may just not have realized it yet. But Microsoft, for instance, we have this big partnership with Databricks, and that is a great thing for Databricks, which is a company that services the open source Spark community, and it's a great thing for us because the thing that clouds care about is you're on the cloud, developing on the platform, sort of consuming all of the resources that the cloud provides. What the actual software is that you're running on the cloud, like you should be natively providing things like as the cloud provider because like there are holes in the ecosystem and like you can see the future, like you want to like provide useful tools for folks. But like where there's an open source thing, like absolutely you should provide it and like provide it in a way where you're contributing back to the community, and like we should be friendly with all sorts of companies like Confluent.
So Julia, from a Slack perspective, how do you think open source licensing and it evolving plays a role in Slack adopting open source software? Does it matter, or does the community matter?
So we use a lot of different open source technologies. For example, if you use the desktop application, we use Electron to develop that. Obviously, Electron came out of GitHub and is now at Microsoft. We're very, very active in that community. As very heavy users, again, at scale, deploying quickly, we have to have a really tight relationship with not only the current roadmap, but the future roadmap. And part of that is us contributing upstream. Another example is Vitess. So Vitess is an open source technology that came out of YouTube to heavily scale and shard MySQL. So behind the scenes, Slack is a MySQL shop. We're, again, very close with that community. We've pushed a lot of patches upstream. We're working very closely with the company that spun out of YouTube to then productionize Vitess and potentially sell services with it. So again, we cannot operate technologies at our scale without that direct relationship. And I'll talk a little bit, too, about often some of the technologies we're using. For example, I had talked before about Hack and HHVM. Some of those technologies were developed in places that had fundamentally different infrastructure because they came of age at a different time. Like, obviously, the Facebook infrastructure is very different than the type of infrastructure, at least right now, that we're running at Slack. The same thing for Google. A lot of great stuff that has come out of Google is based heavily on Google's internal infrastructure. And since we run different infrastructure, since we might use a different containerization strategy, we are going to have to change and modify some of those technologies. And the only way that we can do that successfully is to have that relationship with the community. And then ideally, the next company that comes along that might be completely cloud native, running in the public cloud, they'll be able to take advantage of some of the patches that we've pushed upstream and the influence of thought that we've had with those communities about how do we then take these technologies and apply them in totally new places. We use Kafka, big users of Kafka internally. We really love it. And there's a lot of different new and interesting use cases we're exploring with Kafka that probably, we didn't even exist when Kafka was in the genesis of Kafka. And so I think it's really exciting to think about the ways that these technologies can be used. But all that is very predicated on having the relationship. Mm-hmm.
That's great. So switching gears a little bit, Martin, in your book, you explore a lot of the foundational building blocks, right, of data infrastructure, how things come together, right, to build data-intensive applications, right? Looking into the future, in the next 2 or 3 years, also some startup ideas here. Like, what do you think is missing? What are we going to see in terms of gaps?
Yeah. So there's one thing that I hope that somebody will do. So I feel like something like Kafka gives us something like a 21st century equivalent of the Unix pipe. So it gives us some mechanism for getting some data from one thing to another thing and to tie those two things together, and it provides a common interface that allows very different types of systems to talk to each other. And what I don't see yet is the things built on top of that. So what is the 21st century equivalent of the Unix shell? Like, we have the pipe, but we don't yet have a way of quickly and easily plugging things together in a way that they just slot together in the same way as you can do grep pipe, awk pipe unique, and such like on a Unix command line. So that's something I think a lot about. Related to that is, like, I see a lot of opportunity in moving away from the request-response model that we're so used to it from HTTP that we send a request, we get a response back, and then what? Like, if the data changes on the server, don't you want to be notified? Because like the thing you just got in the response is outdated by now. So really what we want to move towards is a more publish-subscribe paradigm where you can query the state at some point in time, And then afterwards, you just keep listening for updates if that state changes. It seems to me like should be a very natural way of building systems, but the request-response way of thinking is so ingrained in all of our libraries and all of our programming languages that moving...
And even in things like front-end frameworks. Right?
Absolutely. I mean, like what I see exciting is like tools like React, for example, kind of have a bit of this notion that you're getting state updates, which may be coming from a server or maybe coming from the user's own local input, which updates some state, which is then re-rendered in the user interface. So we've kind of got a bit of a stream flowing there on the user interface side. And we've got streams flowing with Kafka on the server side. But there's still quite a gap between those two. Like, what is the programming model in between those two? And that is, I think, something that's going to be really important in the future, and maybe one of you will figure out.
We're starting to transition from. So if you use Slack on a desktop computer, we open a WebSocket and we send a lot of data back and forth. We then transitioned to more of a request-response model, but the ultimate place that we're going is publish-subscribe. And we're starting to use React. And the ability to scale our services and scale our product with that type of model is substantially better. Yeah. But it's a very different type of technology, and it requires a different culture, too, for how you think about, how you do development, how you debug it, all of those things. So, yes, it's the future.
Yeah, and in an interesting way, like it can even, like if you do it right, it can eliminate complexity. Like you can sort of get rid of most of your mid-tier or like all of it, and like nobody loves mid-tiers.
So with some of you here, I would like you to speculate on the future a little bit. You know, if you look just 5 years in the future, what is hype and will die down, and what are things that will live on? As a developer, what is my experience going to look like when it comes to data technology?
Who do you want to start?
I would love for you to start.
Yeah, so, you know, I think, like, you all are sort of in the right place talking about the right set of technologies right now because, you know, we were talking about this backstage. Like, one of the things that I think we're all going to see over the next few years is the next emerging computing platform is really IoT. And you know, we already have like something on the order of 12 billion IoT devices connected to the internet, and Gartner and our own internal data says that like that's probably going to start increasing by about 10 billion devices a year with perhaps some acceleration, and so. Like as you get this sort of ubiquity of IoT devices, like these sort of connected things that are everywhere, they do most of their work by sensing the environments that they're in. And what that means is like a huge amount of additional data. So like if you think about the thing that's made the the web work, sort of really well, just sort of in terms of this. Data, machine learning, sort of engagement data loop that we've got right now. Most of the data is coming from, like how all of us are engaging with internet products. But like pretty soon, like you're going to have maybe orders of magnitude more data than we've ever created, as hard as that may sound, because it's coming from these high bitrate sensors that are in this like ridiculous proliferation of devices. And, like I think streaming sits at the very center of the application architectures for these things. Moreover, like you're going to have, like there's just several orders of magnitude improvement in AI inference capabilities. So like how cheap can you do, can you run a ResNet 50 model to do computer vision? And like, sort of turns out in a few years it's going to be pretty cheap. Like you'll be able to, like for 50 cents, put a chip on a, like a consumer grade price that'll be able to run those models and sort of transform a, like high bitrate raw, like video stream, for instance, into a semantic stream of AI events. And so, like I think your life as a developer in the future is very likely going to look a lot like, where many of you are right now on the cutting edge, where you've got microservices, but they're running in, some device that's sort of sitting out at the very edge of the cloud. They're going to be doing inference, but the inference is going to be taken care of for you by the environment, and you're going to be writing these applications where you're manipulating data streams, and sometimes it's going to be like streams of sort of AI inferences that you're building your apps on top of. So that's sort of my 5-year view of things as it relates to this part of the world.
Very interesting. So Jay, at the end of Martin's talk, he showed that we have almost the foundational kind of building blocks of what a database entails. Speculate on the streaming database. Is that a thing that we will get to see in the future? Will all those building blocks come together as a streaming database? And then what happens to the relational database then?
Yeah, I think that's a great question. I think we're actually seeing kind of the emergence of really a whole new platform here, and it's kind of coming from the bottom up. We have the building blocks. It's really just now getting to large scale deployment in a lot of companies in different areas, and whole new things become possible and whole new problems arise. We were talking about this backstage that LinkedIn had all this data that was available through these Kafka streams, and suddenly there was all those new problems that were created as a result of that, and new tools that came on top of that. And I think that's one of the most exciting things in this space, is kind of seeing how this plays out as different companies really move towards this in different industries, and what does it do to how a bank is built, or how a car company operates, as they suddenly have these sensors in all the cars. What happens in the insurance industry. I mean, you can look across all these different types of companies and how they operate, and how does this technology play out. And I think we are seeing this kind of blur from the stream processing space. As you're getting the ability to represent the evolution of tables of data and put that together with kind of the events and what's happening in the world, and really build on top of those abstractions at a much higher level. It is starting to look a lot more like a database, depending on what the definition of a database is. I have no idea how these things play out. Usually, technologies never really go away, right? And so I think the focus for this ecosystem, I think, is very much this kind of event-driven space. I don't think it means all the other things disappear, but I think that's going to turn into this huge platform at the center of companies. I think there's a whole ecosystem emerging around it, which is a cool thing to watch.
That's a great point, and a good point to end the panel here. Thank you so much, Martin, Kevin, Jay, Julia. This was the best panel I've been part of. Thank you so much.
All right, Neha, Julia, Jay, Martin, Kevin, thank you. That really was a great panel. Before you file out, see if you're leaving already for the break, you're going to miss some important news, which is these 2 dates. The next Kafka Summits will be New York, April 2nd. Shout out to New York, and London, my London people. None of you here, okay. May 13 and 14. That's true. You're from London, so you don't shout. What was I thinking? And of course, there will be one later in the year as well. But these two for springtime, these dates are locked in. Write the appropriate one in your calendar. Block off the time. I hope to see you there. Session starts at 10:30. Go get yourself a drink of coffee. I am going to get some tea. Thank you. Enjoy the day.
Thank you for attending Day 2 of the Kafka Summit San Francisco Keynotes. We'll enjoy a networking break before starting sessions at 10:30 a.m. Then we'll break for lunch at 12:05 p.m. Please check your mobile app for all scheduled details. Enjoy the day.